Morning. Okay, on the board is today's attendance question. We pretty much finished the content for chapter 11. We have scheduled a test over chapter 11 for this Thursday. I hope that you still remember what's our plan. This is a question from section 5. It's question for how do we determine curvature. We have two different formula. Formula for when we have a formula y equal to fx, how we determine the curvature if it's a one-dimensional function. And here we have a vector value function that's in 2 dimensions. So I put the formula up on the board. The curvature should be calculated as the basically the numerator is the second derivative, second derivative and first derivative matrix, the informative for derivative matrix. The determinant of the matrix is the first derivative for x multiplied by second derivative of y minus the second derivative for x multiplied by the first derivative for y. So that's the x prime times y double prime minus x double prime times y prime. That's the numerator. The numerator is the magnitude of the first derivative factor. So the r prime and find the magnitude of R prime and cube that. That will be the denominator. So that's the curvature calculation. And I had formula on the board. I also find both the derivative for x and y, both derivatives, the second derivative for x and y. And you can see if you multiply these two with 4, 2 times 2 is 4. And then 2t times 0 is basically 0. That's why the numerator is 4. Denominator is the magnitude of R prime cubed. So you realize that we need to know the t value if we want to determine the curvature. Here is a point. We need to find the curvature at 0.11. Okay, and then at 0.11, exactly what was the t? You can set that equation, which goes 2t minus 1 equal to 1. T squared also equal to 1. You solve for t. And you can see the solution gives you t equal to 1. So we should identify the curvature when t equal to 1. And right there, we have a formula, and you make t equal to 1. Okay, then denominator is root of 8 cubed. Numerator is 4 over. And then you can see some common factors. We cancel the common factor, then you can start searching the curvature, forming a number. I'll let you to finish the calculation. You guys let me know what was your answer. If there's anything else we should explain, here's our formula. That is the formula that we're going to find those two. The t equal to the curvature formula. Then you should be able to calculate the curvature. All right, if you already have the answer, let me know what was your answer so I can report the attendance. Let me go back to the page so you can see whether your answer is being recorded.
And I'm still trying to write down the equation.
Okay, yeah, I can go back to the page of the equation.
Oops, are you back? I'm not.
That's curvature formula in the block. And then based on our question, we need to find the x prime, x double prime, y prime, and y double prime. And that's how we form the curvature equation in the brain. And then we also have to calculate those numbers. We do have to simplify the number. I'm just writing down. So you guys have to compare which number is the right number. Yes. Thank you. No. So let's see, we finished the calculation. If you put in t equal to 1, we have the curvature equal to 4 over root of 4 times 1 is 4, so 4 plus 4 is 8. And that's cubed, right? To cube a root of 8, you get 4 over 8 root of 8. Because root of 8 equal to 8, so that cancels one of the square of 8 equal to square root of 8 equal to 8. That's what we have. And we can certainly combine or reduce 4 over 8 is 1/2. That's really 1/2, 1 over 2 root of 8. 8 has 4, so 1 over 2, and then root of 8 is 2 over 2 times root 2. So 8 equal to 4 times 2. So the 2 stays, but the 4 gets out of the roots, give you another 2. So combine the 2 times 2, we have 4. So that's 1 over 4 times root 2. That's what it is. I'm trying to make it smaller so you can see how it is. So the final answer should be 1 over 4 times root 2. To double check your calculation, there are some simplification that we have to do. Not to forget. Right, yes. So please take notes if you are not sure about the process. And there's more the reason that we need to um, write it down and analyze what leading to the right answer. So far I found 20 answer. Hope that recorded everybody's attendance. And then for the one that's missing, I think that would be the missing person. Attendance. Answer should be B. Do you have any homework question you want to talk about before we start? Any homework concern, any difficult questions? So we're doing okay with the homework so far? How many of you finished all your chapter 11? Okay, thank you. So we realize that you all due this Thursday, so all chapter 11 homework, I reset the due date. So make sure you do it before Thursday's. So we'll be prepared, and the whole point of the homework is to get us ready with the learning content. So I can send the dates, so they're all due the 18th. 17 was the. Okay. So 18 is the one we have tested. That's why most of the exam due on the 18th stuff with section. Right, we're gonna move on to chapter 12, and today we're gonna continue with 12.2. Last time we introduced multivariable functions, so here we're gonna talk about, now that we know what it is, a multivariable function, and how do we do calculus with it. So this is a main multivariable calculus now, because in chapter 11 is a vector value function, every function in the component form, there's still one variable function, being the variable, the t would be the only variable. So what we were studying in chapter 11 is several, sometimes two, sometimes three, of a single value function. And chapter 12 is the first time the function that we're studying have multiple variables. So section 2 is talking about limit and continuity multivariable function. So with all calculus, kind of like with calculus 1, the first section in calculus 1 is how do we determine limit. With limit, we can start talking about continuity. When we have continuous function, we'll consider finding the slope of the tangent, which will be the derivative. So everything starts with limits. Right, so we're gonna have the new epsilon delta definition for limit. So when you see limit of a multivariable function, we start with two variable function. Then the variable has two number, x value and y value, and the domain is not on the number line. The domain is not part of the number line; it's going to be part of the plane. So we have a two-dimensional situation that we're talking about. Some of the topic on this page, kind of like a portion of the topology class that you have. We talk about open disk. You can talk about number belong to a set or on the boundary of a set. So these are all kind of related to topology. So first we define what is considered open disk in the two-dimensional space. An open disk is centered at a point x0, y0, with radius r is a set of all the points such that the distance from point xy to the point x0, y0, they're all smaller than radius r. And that's what we mean by a disk, an open disk. So basically use a little circle radius r to identify that region on the two-dimensional space. Now, why do we talk about open disk? We kind of use that open disk as a way to label distance. So things are close by, you can cover them up with a small disk. Things are further away from it. If you want to cover both points, you have to use a bigger disk. So that's kind of using a disk of certain radius, we're able to quantify the distance. That's what it is. That's the whole purpose of defining an open disk. Then let's talk about a random set. So S is a set of point in the two-dimensional space R2. A point P in R2 is a boundary point of S. If all open disks centered at P contains both point in S and both points not in S. When you try to draw a picture, it's very easy to understand the whole point. Let's say you got a set of number. Oh, okay. And if the marker works, maybe I'll draw on here. Set. First, we get a blank space. Let's say this is our set of point, which try to make it irregular shapes. That's all the points inside the gray is all the point inside the set S, and then the check different color. And the set S is an initial letter for a set. And then you can see the dark edges. Edges is a darker color. Suppose we got a point on the edge. See here. So then when you try to draw open disk centered at this point. Okay. And no matter how big or small that you're drawing the open disk cover the point, you always have point that is the disk, the point in the disk, the open disk will have some part that belongs to the outside of the set S, some part that belongs to the inside of set S. And this kind of point, we call it boundary point. So we give it a really specific definition of what's being considered the boundary, what's being considered the interior point. All right. Boundary point, the opposite will be the interior point. A point P in S is an interior point of S. If there's an open disk, there is. We don't need many. We just need one. If you can find one open disk that contains P centered at P. That has only point in the only point in the S. So, for example, if we look at an interior point. This set, say, to this point. Okay, so we're able to draw a really circle. Supposed to be centered at that point. Okay, then that circle, all the point in that open disk will only contain point inside, only interior point S. Okay, do you need a drink?
Hold on, I see.
So that's the whole idea. So we are using possibility of able to having open disk center at point P, possibility of it have only point inside interior point, or have no matter how you draw the circle, the open disk it contains point outside the open disk contain point outside S and inside S. If all this is turned out that way, then the point must be a boundary point. So we're using a very specific definition to differentiate interior point and boundary point. Are we okay? Any question? So it's definition that differentiate clearly what's a boundary point, what's an interior point. And we define an open set. Set S is open. Doesn't matter what's the shape. It doesn't have to be a circular shape. It could be any irregular shape. Set is called open set if every point in S is an interior point, which means you strip off the boundary point. You don't contain any boundary point, only contain the interior part, meaning that this is a set where the boundary is fuzzy. You try to not include any point, but somehow you include all the point inside S. And a set S is closed if it contains all its boundary points. Any question? I would say a set that's closed, so it has clear boundary. So since it got contain all the boundary point, I think a closed point would most likely has to be bounded because you have a clear boundary. An open set could be infinite, so you could extend to infinity, and infinity is considered a boundary that's open. Right here. So we're going to talk about bounded set. A set is bounded if there's a m is a radius of the disk, such that you can find M large enough so that the open disk centered at the origin with radius M contains S. A set is not bounded, bounded is called unbounded. So if you cannot find such open disk, then the set must be unbounded. So what's a bounded set? For example, the one I'm drawing is a bounded set because let's see the origin is over here. Okay, and we can draw x-axis and y-axis. Going to the origin. X-axis. X-axis and y-axis. All right, so we can draw a circle, an open disk terms. You see, you can draw, even though the region, the set S is really large, but you can always try to get it large enough. This. Oh, that's not large enough. Okay. See, space is large. Trying to set the stage for a larger circle. Okay, so because it's bounded, I can always find still not large enough. Trying to make the center at the origin, yes, also covers the set S. So that's how large it is. So then the M that we're saying is a circle, an open disk. That center at the origin have a radius M. Yes. As long as you are able to, you're able to do this, then the S itself is being covered in that open disk as the bounded set. If we cannot find such things, then it's not bounded. And that's how we define bounded and unbounded. This is all a conceptual, but these conceptual made some of the definition more clear, and this is why. Right, let's look at bounded and unbounded about boundary domain of the set of development. And the reason that we are talking about all these terminology is because that made it possible for us to determine domain and bounded and unboundedness. And therefore, open disk also helps when we try to look at limit and continuity. All right, here we get a function as two variable function is root of 1 minus x squared plus y squared. You can also try to determine the we determine the domain before, determine if the domain of the function is open, closed, neither, and if it's bounded. The answer is already on the board. We find the domain last time. That is the domain of a function is determined by the definition of the function itself. This definition is taking square root of 1 minus x squared over 9 minus y squared over 4. So the square root calculation is only one that brings a concern of the possible x and y value that we could plug in. Because essentially the square calculation, the subtraction, all these, you can use any x value and y value. The only concern is the square root calculation. So we have to make sure that under the root is a value that is positive. So, and that's our topic when we try to determine the domain. So let's try to determine the domain, then we'll talk about whether it's bounded or unbounded of the domain. So here is our function. And to make it well defined, the number that we take square root of, it has to be bigger than 0 or equal to 0. So that has to be simplified for it to be properly defined, because taking square root of negative number will make it undefined. That's the domain. Using this, we bring the negative term to the right side of the equation and switch the direction of the equality. That's how we get the x squared over 9 plus y squared over 4 is less or equal to 1. Now, all these points that satisfy this condition live inside the ellipse, and that's the domain. Right, and you can see that was the ellipse that looked like this. It has a radius of, you see the x squared over 9 if it equal to 1 and the x squared equal to 9, and then you have 3 and -3. So the boundary for the x value, y squared over 4 has to be less than or equal to 1, so y squared is less or equal to 4. So the y value is bounded between 2 and -2. So then the domain of the function, the inside is ellipse. The drawing is not perfect. Right, and then this will be the domain. You see, it is bounded because we could easily draw a open circle of radius 3. Doesn't matter, 3 or 4. Draw a circle like this. The radius could be 3. So we can find the open disk that contains the entire domain. Therefore, the domain is bounded. That's from the definition of the boundedness. Also, see that equal sign. Whenever the x squared over 9 plus y squared over 4 equal to 1, that was the boundary of the ellipse. So we are saying a closed set. The domain, this set, we're not using S, we're using D here because of the domain. This set of a value or set of points on the xy plane, the boundary is included, so we have an open set. Any question? That should answer the entire question. It's about the domain, whether it's a closed set or open set or neither, whether it's bounded. So the answer is bounded and closed. There. That's the first example. And we might see a couple also question about the domain. And this one, you can see we want to determine the domain. This is something we determined before. The calculation has subtraction and division. Subtraction is an operation that can be done for any number, so there's no domain concern. Division is not. So when we have division, we want to make sure that the number is not 0, and that take out points that whenever x equal to y, those points cannot be the domain. So the domain of this function will be all number of x and y pair, except when x equal to y. So as long as x is not equal to y, it's okay that it will be in the domain. So in this case, obviously the set of point is open because the boundary point is not inside the domain. And on the boundary, the x equal to y line will be the boundary of the set, at least part of the boundary. So that part is not in the domain. Therefore, we are looking at an open set. Another thing is the boundedness. It's not part of the question, but the domain definitely is unbounded because it includes any large x and arbitrarily large x value and large y value. And therefore, we cannot find any open circle that cover the whole domain. At least not the finite radius circle or finite radius disk. Any question? So that is what we were just talking about, open and close, or whether the set of points is bounded or not. Limit. Now, the limit of a two-variable function is L, as long as given any epsilon, you're able to find a delta, also delta, that's a radius, such that if xy is in the open disk centered at x0, y0 with radius delta, there is f of x minus L is less than epsilon. So meaning that we're able to make f of x and L very, very close. So close that their distance is smaller than any arbitrary given epsilon. How do we make them close? As long as we make x and y close to x0. How close they should be? Closer than a certain delta. This delta, we need to find it. I mean, if you say they exist, you gotta determine what is the delta in relation to epsilon. That is arbitrary. So epsilon is arbitrarily given. But delta is something we have to search for if you were trying to write the epsilon delta definition for the continuity. So if there's anything that is special, is this open disk centered at x0 with radius delta, that you might have to write a distance formula between x0 and x0, y0, and xy to prove the limit like xy approaching x0, y0, how we prove that approaching process by the fact that they're all the same. Okay, so that was a visual example. Basically, f x and y, z would have in fact represent the surface. Here we're drawing that surface. The surface is equal to x, y surface. On that surface, we have a point. Right, that point is represented by x0, y0, and then the z will be f of x0, y0. So that's the x, y, z value for that point. So three-dimensional point. And we're trying to approach that point from all directions on the xy plane. And down here is a projection of the surface onto the xy plane. Both the surface and the xy plane is two-dimensional, except on the xy plane we have the z equal to 0, but on the surface we do not. As the xy, arbitrary xy approaching x0, y0 on the surface, it will approach L if the limit exists. L is a z value here. So that's a three-dimensional image of how this process. The limit is a process. And one point is closer to another point, the limit point. Okay, so briefly with that, I'm going to talk about more on different limit calculation. These are a couple of rules that was correct, verified for the one-dimensional, one-variable function. Here for the two-variable function, number one, suppose you have two limit calculation, one function, two-variable function had the limit of L, another function have a limit K at x0, y0. Here we have a couple of rules. Number one, any constant function, the limit will still equal to that constant number because the function formula has no xy variable. Therefore, the xy approaching the number or not will not affect the limit itself. That's why it's called a constant function. Number two, that the value for individual x value and y value as xy approaching x0, y0, then x is approaching x0, y is approaching y0. That's the identity function. Number three, summation of the two functions, their limit equal to the summation of the limits. So limit value is L and K. And then L plus K will be the limit of f function plus g function. Assuming the individual limit exists, then the summation function will also have limit that exists. Number four, if the function multiplied by a number, then the limit of this function equal to the limit value multiplied by that number. So that means if we have a common factor in the limit computation, that number can be written out of the limit calculation, and you focus on the limit calculation, which is L. And then you multiply by b. That's giving us some calculation hints. Sometimes we can simplify the limit computation by focusing on the little details, bring some common factor outside. Number five, the limit of the multiplication of two functions equal to the multiplication of the limit value. Right, that also indicated. If we are looking at a function, it's actually a multiplication of two functions. We can find individual limit one by one, and then final answer is a multiplication of two. So all these rules made it possible for us to simplify the calculation sometime based on the correctness of the rule. Number six is when we have division of two functions. As long as the denominator has a limit that's not zero, then division of those two numbers is the limit of the division. The number seven, if we have a power function, then limit of the power function is the power of the limit as well. So these are all rules that used to apply to a single variable function. Now they also apply to the two variable function. Any question? So these are properties of limit calculations. Okay, let's look at some of the application of these. We're gonna try those rules. On the left, we have applying the division property and the summation property. On the right, we apply the division property. See how we can see the see. And well, we're going to be careful with zero though. The first one, I think we should do okay. The first calculation is x, y approaching 1 and pi, meaning that x is approaching the number 1, y is approaching pi. So limit value, the y goes to pi, x goes to 1. What was the division? Plus cosine of x times y. X equal to 1, y, that's cosine pi. All right, and then this is obviously just pi over y equal to pi. Cosine pi equal to -1, so that will just be pi minus 1. That finished the first example. The second example, we see a little bit problem, and this is a problem that we use to handle. What if numerator and denominator both approaching 0? X and y approaching 0, and x approaching 0, y approaching 0. So numerator is 3 times 0 times 0, denominator is 0 squared plus 0 squared. We're looking at 0 divided by 0. Okay, and that doesn't mean we do not have limit. It means that we have to have better way to find the limit than substitution. So simply plugging number x equal to 0, y equal to 0 does not work here. Substitution is a first approach with all limit computation. If substitution works, that means the function has continuity. Then if the function continues, everything works out, and that will be it. So whenever a function is continuous, it provides convenience for limit calculation. But if you substitute the number in, things does not work, that the clear reason for that will be the function is not continuous at that pair number. So when x equal to 0, y equal to 0, obviously this function is not continuous. And we have to think about other ways. So one of the ways to do this is to have some relation. Right now we're doing x and y by itself individually. We could make them have such a relation. For example, let's say y equal to kx. So we make x and y proportional. In that case, if x is approaching 0, y equal to k times x, therefore y also approaching 0 accordingly. So this is one way the approaching process can be connected and illustrated, and that also give us less number to work around. So let's see what will happen if we do this. And the limit will be limit equal to x approaching 0, and then y, and make y equal to k times x. And that was a question though. Equal to, in this case, we have, you see this would equal to this if y equal to kx. But then, you see. So this is a special situation of this. That's what I'm saying. This one, and let's see, should equal, but this is a special case. 3 times x and y equal to k times x. So there's k times x right there. Over, this is x squared plus y squared, y equal to kx. So it's going to be k squared times x squared. And we see the benefit of doing this. The numerator and denominator both have x, and they both have x squared. So the numerator has 3k x squared. Denominator have x squared plus kx squared. You factor out the x squared, cancel upon the factor of x squared. You have this is equal to 3k divided by 1 plus k squared. All right, for this step, do you have any concern? Do you have any problem? You see the numerator has 3k times x squared. The denominator is x squared times 1 plus k squared, right? Right? We cancel the x squared, now this is what we have. So we end up having, if y equal to kx, then the limit equal to 3k over 1 plus k squared, meaning that this limit is taking on different value when k have different value. So y equal to kx through several different paths for x and y to approach 0. Along different paths, it seems to have different limit value. And what that answer means, k takes on different value, and this limit is not unique. So approaching 0 from different paths, we are looking at a limit value that's not unique. And not being unique is one of the main things about limit computation. Limit has to be unique. If you know this limit is not unique, you know the limit does not exist. We're able to prove that with that special situation, we realize along different paths of approaching y equal to kx is a line. You go approach 0 on this line in the xy plane, it takes this limit, and then you like k equal to 1, the limit is 3/2, and k equal to 0, the limit equal to 0, and k equal to 5, the limit is 15/26. So when k takes on different value, we have different limit value. That means the whole limit value is not unique. Because it's not unique, and it doesn't affect by the x is canceled, so x is not affecting it. Y is equal to kx, and k is the only thing affecting it, but those paths exist on the xy plane. So not unique, that means the limit is this. So the limit, this limit does not exist. And that's what I sometimes write, and in short, does not exist. Any question? I think in Calc 1 it also in the same way, whenever the limit depend on something, if it's not unique, then the limit does not exist. Limit has to be unique. This is our first example on limit information. Right here, it's easier to prove limit does not exist than to prove it does. To prove the limit does exist, we have to follow the whole epsilon delta definition. To prove it does not exist, all you have to do is choose one path, one scenario. The limit is not unique. And then there is the proof that limit does not exist. Right, that's one. And then and I was already showing one way. The example that we just did is example number 1 to show that this limit does not exist by finding the limit along the lines. Line is y equal to mx, which is saying that saying y equal to kx. So you can see the limit is dependent on the m or dependent on the k. Therefore, limit does not exist. The second one, we want to show this limit does not exist by finding the limit along the path y equal to sine x. Y equal to sine x is a sine curve. It goes through 0 on 2 different sides around the origin. So and we can try that. The second one. So what I'm saying is on the xy is approaching 0. So on the xy plane, right, and here is a point 0, 0. We're seeing xy approaching 0. It could be approaching 0 here, approaching 0 here. It could also approaching 0 this way, and it could also approach 0 the one which had negative sign, this negative sign curve, like this. So it's approaching 0 this way. So that you may have many different ways of approaching a single point. This is what's making two-dimensional limit complex. Because we're facing different paths where x and y can approach a single point. It's a lot easier in one-dimensional because in one-dimensional you have a single number line. Here you're going to say x is approaching 0. Then how does it approach 0? From the left or from the right. So in Calc 1, the limit is left limit, right limit. That's it. There's no third way to approach 0 from anywhere. So they're just trying to explain why we created so many different weird ways to find the limit or prove the limit does not exist. So we're going to do this. So this equal to, with the condition that we're making y equal to this function now. So when you do that, assuming y equal to negative sine x, so then x is approaching 0, and y is equal to negative sine x. So it doesn't matter which way xy is approaching 0, the limit is supposed to be identical. So we have this freedom choosing a single path, right? Doesn't matter which path it is, this got to equal to this. Even though there may be more than one way to approach 0, but if the limit does exist, it's supposed to equal to it anyway. So if we want to prove it does not exist, we only prove at one path the limit does not exist. Then I kind of break down the logic. So sine x, and here is negative sine x. it's multiplication, so maybe I'll type it better. So the numerator will be sine x times negative sine x. And whenever you have negative sine and negative angle, the negative goes out. So it's negative sine and then x sine x. That's what it is in the numerator. And then the denominator is going to be x plus sine x. So the denominator is x plus y equal to negative sine x. So x minus sine x. That's what it is, the denominator. Right, so here we're going to try to prove this limit does not exist. How do we do it? Now what it does, making y equal to negative sine x, is that we are turning a bivariable, two variable limit calculation into a one variable limit calculation. That's why it's easier for calculation. Now we can apply L'Hopital in this situation. The numerator and denominator are both approaching zero, so we're looking at 0 divided by 0. So that we can find derivative of the numerator, derivative of the denominator, maybe that limit will be easier for calculation. So here, the limit of in the numerator, we have to apply chain rule. Derivative of negative sine is negative cosine, and then there's no change to the inside function according to chain rule. And then we're going to multiply the derivative inside function. That will be derivative of x equal to 1. So 1 times sine x. Plus, we have to apply the product with the inside part of the multiplication, plus x multiplied derivative of sine, which is cosine of x. So that is a derivative of the numerator, right? According to L'Hopital, this is the denominator also has to be differentiated. And that's slightly easier. Derivative of x equal to 1, derivative of sine x equal to cosine of x. And we still can't when x equal to 0, when x approaching 0, denominator is 1 minus 1. It's cosine 0. We still can't do it. Cosine x approaching 0 is cosine 0 approaching 1. So we can see this limit is not 0. That's not going to be a problem. Right, and then we have to do a L'Hopital one once again. Those are still 0, right? This is a sine 0, 0. This is a 0 times 1. That's still 0. So that will be a 0 multiplied a 1. So numerator is approaching 0. Denominator is still approaching 0. To prove the limit does not exist, we have to do L'Hopital once again. So apply L'Hopital one more time. Okay, so here we are in division. Right, one derivative of 1 equal to 0, derivative of sine equal to negative sine. So the denominator have a sine of x. And then we're going to find derivative of numerator. In here we can do a little trick. This part of the function is negative cosine of 0. It approach 1 is not one of the part of the factor that will affect the whole limit calculation. You can separate them into two limit calculations. This one have a limit value when x approaches 0. This has cosine 0, which is negative 1. So that's not affecting that will always be negative 1. So we don't have to. I'll consider limit being negative 1 in that part. In this one, we do the L'Hopital. Well, I'm just trying to simplify the calculation. I don't want to do another product rule to make the numerator even longer summation. So instead, I'll leave the negative 1 as calculated form, and I'll go ahead and find the derivative of sine x plus x cosine x. Derivative of sine x is cosine. Derivative of x plus cosine is derivative of this cosine. And then plus this time we're going to keep x and find derivative of cosine. That's negative sine, so it's negative sine x. Right, and that will be the derivative of the numerator. And then we can look at the calculation. You can see if x approaching 0, I didn't write the x value. We should write limit x approaching 0. Every limit notation, there should be x approaching 0 below it. If x approaching 0, denominator is sine of 0, which is 0. numerator is cosine 0 minus 0 times sine 0. That will be 2, right? So -1 times 2 is -2. So that will be -2 over 0, which is what's making it undefined. And that's why it doesn't have. So this, along this path, this limit is undefined. Because the numerator approaching 0, numerator does not. And they we applied the L'Hopital twice. And in the middle of it, we also made one of the factor calculated rather than carry over the product. This is my proof of it. Any question? I think we can only do this. I'm trying to make it more convenient, but we can only do this if you have a multiplication. And also this part has not been a 0. If it's 0, you have to combine with that one. And you have to do the L'Hopital together. If it's not 0, like 5 or 2 or 1, you can calculate it. So then you get rid of one part of the calculation that we have to differentiate. And that's the example to show limit does not exist using one of the special paths. You can try other ways. This function is kind of difficult to invent with alternative ways. So that's why the text would print out that as an example. Okay. Any question? So we have a couple of examples on the limit computation, and this is another calculation question. All right, you can see that this one, the first example is showing whenever the numerator and denominator has polynomial of the same degree, denominator degree 2, degree 2, and this is the degree 1 times degree, that's also degree 2. When the x and y both approaching 0, that one does not have a limit. However, when the numerator have a higher degree, it's a different situation. So here, if you want to calculate this limit, and we can see that this limit actually exists. Okay. At least we can try the earlier situation. What if y equal mx or y equal kx? If y equal mx, and we see this limit is equal to, the numerator is going to be the limit of x approaching 0. Numerator is 5x squared. 5x squared times y squared, and y equal to mx, then y squared will be m squared x squared. And see what happens to the denominator. The denominator has lower degrees. You have an x squared plus m squared x squared. X is approaching 0, obviously. And this is equal to, and again, this is always equal to this, no matter, because this is a single special situation of the approaching. Right, so this will equal to limit of, you can see the numerator is going to be 5x to the power 4, and then m squared. Denominator is going to be x squared factored out, and then 1 plus m squared. And then the common factor will be x squared. This cancel x squared. And you're going to end left with x squared after the x squared canceled. So numerator will be 5x squared m squared over 1 plus m squared. And then we have to let x approaching 0. If x approaching 0, because the numerator is multiplied with 0, it's only equal to 0. So with the special path, it doesn't depend on m. The limit value equal to 0 if we let y approaching 0 along a straight line. This is relation between x and y. We're approaching 0 along the line y equal to mx. So it doesn't matter which path you're approaching, you're still getting to a 0. The z value equal to 0 that we're arriving at. You can also try other paths as long as you're allowing the y approaching 0. For example, I cannot choose a path y equal to 2 to the power x, because if x approaching 0, y approaching 2, we don't want at y approaching 2, we want x equal to 0, y equal to 1, right? So we don't want y to go to 1, we want y to go to 0. So that obviously is not a good path to choose. You can choose any other path that y is also approaching 0. For example, we can try the earlier example. You can make y cosine x. And you can see, if you make y equal to mx, this is the line. Goes y equal to mx, m is the slope. And what I'm doing right now is this, right? Y equal to sine x, and then sine is approaching 0 right here. So around 0, y is also approaching. So basically, whatever path you choose, you have to have the point 0, 0 on that path. Okay, then at y will actually approaching 0 together as x approaching 0. So you have to have that continuity going on in the substitution. So if we do that, what will happen? I'm just trying to prove that whatever path you choose, the limit will still equal to the same limit, which is 0. So we will have 5x squared times the y squared. Right now, the y equals sine x, and you have sine square x over x squared plus y squared, x squared plus sine x squared, and then x is approaching 0. Right, so how did this one calculate? I guess is a little long one. I should choose that pass. The numerator have to do product, so I kind of expect some time spent on trying to work it out. We have to do L'Hopital. Numerator is denominator is going to be 2x plus 2 sine x cosine x. Okay, and then the numerator is going to be 5x squared. We differentiate the sine square. You have 2 sine x cosine x plus this time we differentiate the 5x squared to get 10x and times sine x. Okay, you can see what happened there. The sine x is a common factor. We cancel the common factors. Oh, it's not now in this case. This is sine x. So it's even worse. The numerator is approaching 0, denominator approaching 0. We have to apply L'Hopital again. Thanks. Do we have a common factor? We can factor out the 2 from the numerator and factor out its 10 from a 2 from the denominator, a 10 from the numerator, and else. Yeah, we have no choice. We have to apply L'Hopital twice. I am very sure that the limit would be 0 after we apply L'Hopital another time, because this one will give you a 2, and the numerator definitely will still have 0. So it should be 0 divided by 2. But I want to skip that process. All right, so how do we do it to be sure that the limit is 0? We see that between the x and y, instead of having 2 separate variables, and when you allow x and y both approaching 0, we can make x and y a better representation. X equal to r cosine theta, and y equal to r sine theta. So we're representing the xy location with basically the polar coordinate. What's the benefit of doing this? You see, if x and y do approaching 0, then the r has to approach 0, and angle would be you can stream off the limiting process. Xy approaching 0, the one you have to make it approaching 0 will be the r approaching 0, right? Make xy approaching 0, then the only thing that has to approach 0 will be r. So the whole idea of having the variable change is that we can isolate the variable that we work with. Instead of worry about both variables, you can focus on a single variable. And if your limit only depends as a single number, it doesn't depend on theta, then we have a limit. If the limit still depend on theta, and for different theta, that means a different path or different angle, then the limit is not the same. Then we know we have a situation the limit does not exist. So I feel like this change of variable is a lot better than this one, or the one I was this one. I was randomly showing that past and realized how hard it is with L'Hopital's rule. You have to do multiple application of L'Hopital's rule. So let's try this with verifying that limit is actually equal to 0. And let's try again. So this computation, it will equal to limit of this function. We will have 5x squared y squared, and this is our x and y. So x squared would be r squared cosine squared theta. And then y squared will be r squared sine squared theta. And denominator is x squared plus y squared, which will be r squared cosine squared theta plus r squared sine squared theta. We will make r goes to 0, and that's the only thing that you have to do if x, y is they're both the distance between x and y and point xy and point 0 is getting smaller and smaller if xy is approaching 0. So we can kind of focus on the single variable instead of worry about both. So if xy approaching 0, theta is only an angle. So when we do this, realize the denominator have a common factor of r squared. The factor of r squared, we have cosine squared plus sine squared. Cosine squared plus sine squared theta equal to 1. So the denominator really is just r squared. And the numerator is still the same. But then you can see there's a r squared here and there are r squared. Cancel one of the r squared, the numerator become this. So we can clearly see the reason that it do. Numerator will be 5r squared. One of the r squared cancel is you have one r squared left, and then you have sine. This one would cancel sine squared theta cosine squared theta. And then r approaching 0. Since this one cancel with this, like this two cancel, there's one r squared left. When r goes to 0, this is equal to 0. That's clear enough. Any questions? Oh, are we okay? This is one of the substitution that will make the two-dimensional scenario a lot easier to manage when we try to prove the limit exists or does not exist. Right. The finding part, I think we can do any calculation to determine the limit. This one is trying to, the limit is 0. This is trying to prove the limit equal to 0. Prove it and finding it is two different things. If we want to prove the limit is 0, we have to go by the epsilon delta definition. So you have to study these two, both of the variable part and the function part. And I guess the process of determining the process is not the same as rating the answer. If you read through the answer, proving the limit exists, start from here, when I said let epsilon bigger than 0. That's where the proof started. Let epsilon be any positive number. We want to be able to prove that f(x) is less than minus 0 is less than epsilon by choosing proper delta. And here, to say delta exists, we have to find that delta. And that's all these processes try to prove that. I guess when you do it by yourself, it's not like immediately visible. We have this 5x squared y squared over x squared plus y squared. We want to prove this limit equal to 0 for when x and y is approaching 0. So the mathematical proof. So we're saying that choose for any epsilon that's positive, for any epsilon bigger than 0, we can make 5x y squared over x squared plus y squared closer to 0 by like less than epsilon. We can make this happen by choosing appropriate delta whenever x squared. This approaching, it's the distance between the two. Distance between the two is x minus 0 squared plus y minus 0 squared. It's less than delta. this one. Right, so we're gonna have to find this particular delta that we needed. Okay, so how do we do it? Its relation is this. So suppose we wish to have this. How does that happen? So this is our leading logic, and then we're gonna the process that you want to prove this, and then you have to get this, and then you have to like from here to here. That's the process of trying to find the appropriate delta. So, algebraically, this looked like a 5x squared plus y squared less than epsilon times x value of x squared plus y squared. What we really wanted to have is this. Right, if we start from the direct derision, this is what you have to consider when trying to I think the text was shown by a special radius. Right, I feel like we should skip the proof part. So logically, there are different ways to prove the same limit. When you try to prove the epsilon delta definition, you have to set your own setting. The textbook choose to have a special setup that says 5y squared over x squared plus y squared is less than 5. Whenever the x squared plus y squared is really small, you can make that happen. And that's something that's one proof should make the limit happen. So you have to set some individual setup to make the final thing happen. The proof part there are different. I think this is not how I would prove it. I feel like we would have to limit the approaching part. When x and y is approaching 0, that means this value is already really small. And that's why our textbook was saying if x squared plus y squared is already small, when it's small enough, this will be less than 5. That's assumption. It's already assumption now we have to apply along this. So anyway, since the proof is not our goal, if you are interested, you can go through the proof. And I realize this is not something we would focus on. I feel like if I do it, that's not what I. This is not the approach I will take. But it logically makes sense. Whenever the denominator is approaching 0, x squared plus y squared will be small. So we would say for small enough value, small enough radius, this will work. The 5x squared is 5y squared over x squared plus y squared will be less than 5. Right. And that's really the initial part. The rest of the proof. Let me see. Okay. So that's the limit part, and with this same one, I think if we want to find the limit quickly with most of the bivariate function, the most common thing is use a polar coordinate. I think we went through this. We can make x equal to r cosine theta, y equal to r sine theta to make the limit calculation easier. One of the logic behind this is instead of have to consider the two separate variables by itself, this approach, the benefit will be focus on only one variable. So make r approach 0, and that therefore, if the final answers are related to theta, then the limit is unique, and then we have a limit. If the final answer is still related to theta, you have a formula of theta in your limit calculation in the final number, then the limit is not unique, and that means the limit does not exist. So this could be a very common way to treat most of the two variable functions limit value calculation. And there are a couple of examples in that sense. For example, this one, you can also do the polar coordinate, x equal to r cosine theta, y equal to r sine theta. Then the denominator will be r squared, and the numerator also have r squared. So your answer will have 3 times cosine theta, sine theta in the limit value, and therefore is theta dependent, and that's make it not unique. And then because the limit is not unique, therefore it does not exist. So depending on the path that we choose, that's the reason we say the limit does not exist. And so you can see we are, by looking at different paths and thinking about the variable function, the difficulty in multiple variable function is because it has multiple variables. So the way we study it is try to temporarily lower the number of variables that we have to consider. So it's always easier when there's only one variable that we have to worry about. Let's talk about continuity. So the continuity of a function, you will look at by continuity at a point. If it's continuous at all points in the domain, then the whole function is continuous. So conceptually, it's still the same as in calculus 1. You worry about continuity at a single point, this number 1. So if f is if the limit of the function at a single point equal to the function value, then it's continuous at that point. Second, if it's continuous at all points in that domain in the set, then it's continuous everywhere. So it's continuity for the whole function. All right. So when we actually look at continuity of a function, we often worry about the suspension point. So we're not looking at the continuity. So it's something we have to worry about whether the function is continuous everywhere. It's actually only 1 or 2 points that we have to worry about. For example, this one. The function is being defined as piecewise defined function. So for x is equal to 0, we have one formula. For x is not equal to 0, we have another formula. So in this case, to ask whether a function is continuous at 0, then you will find the limit of the function at 0, and then you will find the function value. If they're equal, then it's continuous. And then for the second function, it looks like if the function would be continuous whenever x is not 0. For all the points x is not 0, it's continuous. For x equal to 0, the first question's answer would already answer that continuity. So if x is the function is continuous for x equal to 0 and x is not equal to 0, of course it will be continuous. So the logic will be answer the first question and then the second question. We'll look at the two definitions one by one. Let's see. All right, so the first question will be whether the function's limit equal the function value. So function limit is cosine of y sine of x over x, and we make x and y approaching 0. Approaching 0, 0. If this is equal, this is the question mark. This is equal to function f of 0, 0. Okay. To answer the first question, you answer whether these two are the same. Now f 0, 0. That's when x equal to 0. You have to use a second formula for the computation. You can see f 0, 0. X equal to 0, y equal to 0 using the second formula cosine 0, which equal to 1. All right, and then this right side of the equation. The left side of the equation is the limit of the function. So we make x equal to 0, y equal to 0. That means this is 0, that's 0, and then cosine y is 1. Okay. So limit of cosine y, if y is approaching 0, is 1. Now limit of sine x, you can see we break this down into a multiplication, right? Limit of sine x over x if x is approaching 0. So then the limit of the multiplication would equal to the multiplication of the two separate limit, we convert it into two separate calculation, then the cosine y is at 0, cosine 0 equal to 1. Now, sin x over x if x approaching 0. I don't know if you remember, what's that limit? Sin x over x if x approaching 0, what is, it's a special limit. Do you know? Equal to 1, right? Sin x over x when x approaches 0 is 1. So this is basically 1 times 1. So then the left side, this limit equal to 1, this function equal to 1. So it's yes. So limit value at 0, 0 equal to the function value at 0, 0. So the function is continuous at 0, 0. Second one is whether the function is continuous everywhere. We only have x equal to 0. So the function definitely f is continuous. Whenever x is not 0. Okay, so and then you can see the first definition is already the definition already right continuity when x equal to x is not 0. Now what about x is x equal to 0 and see if there's continuity and there. So how do we prove continuity if f of like the function limit of cosine y sine x over x if x is approaching x and y approaching 0, 0. If it's equal to f of, we say if f equal to 0, right? The first part is already continuous. Second part, if x equal to 0. If x equal to 0, the function follows the second formula. And then f 0 y, right? It's this. So follow cosine y. Right? We want to know if these two are the same. And turns out you can factor the cosine y outside. Then the sine x goes over x, and the x equal to 0 is 1. So it is cosine y. So the left side it has the limit cosine y, and the right side have a function value cosine y. They're equal. So the answer is yes. So this means why the defined function is continuous at 0, 0. It is also have continuity everywhere because the limit value of the function equal to the function value at that same point. That continuity, again, for continuity, we also have its algebra. If both functions are continuous, the summation is continuous. If the function is continuous, when you multiply by numbers, still continuous. If functions are both continuous, therefore multiplication is continuous. Fourth one, if the function are both continuous and the division is continuous, as long as the denominator is non-zero. And also continuity for power function, continuity for root function, all are well defined, as long as the function itself is well defined. That function for computation is a little more complicated. It depends on whether the computation calls any domain issue. Then that should be most of it for the two variable case. All right, that will be for today. We will continue tomorrow. In the meantime, try to get your chapter 11 done. Have finished them. Question. Let's see for today. Sorry.
Only have two sports.
And that's it.
Can't believe we're separate my dad, please. So I can touch up to you, nothing with.
The next question.
Well, people then I don't.